SwayamPrabha. Digital India. Educated India.
Good morning everyone. Today we will continue with finite element method, and if you recall, we obtained equation 11 via integration by parts, and we aim at evaluating equation 11 on the element of interest. Basically, the element is a triangular element, three-noded triangular element, and we have already evaluated term 1 of equation 11 and term 5. So first term and fifth term we have already evaluated in the last lecture, in the last class. Today we will complete integration of other terms. Now next term we'll take up is basically term 2, and this is integration of heat flux on the confining surfaces. That means on the boundary of the domain. Now if you look at the way we described the grid topology, the way the grids have been generated, the triangular elements are covering everywhere in the domain, but at the boundary, if you look at the triangular elements, it is obvious that line segments of the triangular element are falling on the boundary. That means boundary is covered by one side of the triangle. So all the triangles, those are falling on the boundary. They are covering the boundary by one side of the individual triangles. So basically that means that for the triangular element which is falling on the boundary, we will have Ni, which is basically a shape function at 2 points of each triangle that are falling on the boundary. So when we perform the integral Niq dl, we can write Q integral Ni dl, where I is having a variation between 1 and 2. So then we write in 1 the shape factor, and as usual 2 into area is in the denominator, that is determinant of the matrix. We are taking it outside the bracket. Inside we are getting x into y2 minus y3 into dl, y into x3 minus x2 into dl, and then we are getting x2 y3 minus x3 y2, and we are integrating over the line. And in this line integral we are following the method of Gaussian quadrature, where when the line integral is performed, the points may be identified and weights may be assigned to the point. Here we are we have taken x bar and y bar as those reference points, which are basically mean point between x1 and x2, and y bar is also y1 plus y2 by 2, and then we are performing this integration and having performed the integration and carrying out this algebra, we get q into L. L is the total length of the line element or the line segment, divided by A into area, and these terms which can be reorganized as basically determinant of the matrix. That means again 2 into elemental area. So we have written that QL divided by 4A, 2 into elemental area. So Q into L by 2. And next again, I'm going back by one slide. Next again we substitute ni I equal to 2, so n2, and similarly we integrate n2 shift factor over the line segment, and then again we will find out QL is the length of the line segment by 2. So this integration will give us Q into the length of the line element, and a column matrix half and half. So this is called QB for the element. We have written also LE represents a line element which is subject to the heat flux boundary condition, heat flux specified heat flux condition. So this is the contribution. QB per element is the contribution of the heat flux, and the part of the boundary that where constant heat flux is applied. Now we integrate the third term, which is basically the convective heat loss. So we have written here Ni shape factor, H into H is the heat transfer coefficient, T minus Tf is the ambient temperature, dl. Now here again T is substituted by integral Nj Tj. Nj is the shape factor, and here also the triangular elements which are falling on the boundary, these are all line segments or lines, and these are having 2 points, so obviously 2 shape factors and associated the column vector for the temperature. So it is J equal to I to 2 Nj Tj summation minus Tf. Now we perform this integral in this manner, J equal to 1 to 2, and this is integrated. So Ni and Nj getting multiplied, so H Ni Nj dl, and this is a column vector. Here only 2 elements are there, and this is H into Ni Tf, the ambient temperature. This is also known, will come outside the integral and dl. Now if we perform this 2 integrals, finally we will get H1 Tj minus H2, and H1 is what? H1 is HL by 6 multiplied by matrix 2 1 1 2, and H2 is HTF into the length of the line segment, half and half, again one array, basically a column matrix. So now evaluation of H1 and H2 we will discuss in the next slide. So H1 is, as we said, integral of H in I and J dl, and we can write as N1 1 minus y by L, and then N2 will be y by L. Very, certain shape factors then with point 1 and 2. If we say 1 is 1 minus y by L, 2 will be y by L, so that summation of the shape factors on anywhere on the segment has to be 1. That is a property of the shape factors. So we perform this integral. You can see n1, n2, n1, n2. Now when we multiply, it becomes n1 square, n1, n2, n2, n1, n2 squared. And from here, after evaluating, we get L by 6, and this shape factors finally contribute into 2, 1, 1, 2, this matrix. So this is basically evaluation of H1E, and then we'll also find out H2E. H2E is H Ni TF dl. Integral of H Ni TF. As I said earlier, TF is known and will constant rather here will come outside, and then it is integration of Ni dl. So H TF into L, total length of the line segment, half and half. Basically Ni evaluation, when we integrate Ni dl, again this integration through Gaussian quadrature philosophy has to be followed, just like what we did for the term 2, and we have seen there the final quantity becomes twice area of the line element divided by 4 area of the line element, twice area of the triangular element divided by 4 area of the triangular element, 2a by 4a, that is half and half. That forms the column matrix. Just not to confuse you, I will go back once to show this integration of Ni dl, how we did in the first slide. So this is integration of Ni dl. What I said, finally we got whatever is a constant term, outside that this is 2a by 4a. So basically we get value of this integration as half. So here also we perform a similar integral, HTFL, we get outside the array, and within the array we get half and half. So therefore, together with H2 and H1, we can account for the convective contribution. So H1E and H2E are the elemental contribution of convective energy transport, convective heat transfer. All the above mentioned elemental matrices and the vectors have been obtained from the integration of the expressions for N1, N2 and N3 as defined in the equation 11. So now we can say that all the above mentioned elemental matrices and vectors have been obtained from the integration of the expressions for n1, n2 and n3 as defined in equation 11. Let us, for the present, consider a problem with no radiating boundary. So we have considered all the boundary conditions, but radiative boundary condition we have not evaluated. We'll evaluate that little later. So let us imagine a domain which does not have any boundary where radiative heat transfer is taking place. Thus, the nodal equation for any of the nodes of the FEM can be constructed by approximately summing up the contributions from the heat conduction term, heat generation term, convective boundary terms, and the heat flux boundary. If the points are such that few are lying on known, few are lying on a boundary where temperature is known, then obviously for those points we will prescribe known temperature. For example, Ti will be Tb. For the node I, where Tb is the prescribed boundary temperature. So that is how the contributions will come for each term in equation 11 evaluated on elemental triangle, on individual elements triangles. To find the properties of the overall system, we must assemble all the individual element equations, that is, to combine the matrix equations for each element in an appropriate way. Please note this very carefully, such that the resulting matrix represents the behavior of the entire solution region of the problem. The boundary conditions must be incorporated after the assemblage of the individual element contributions. So individual elements, if there are 50 elements, from each 50 element we will get one matrix multiplied by T1, T2, T3 equal to some known vector. Now we have to get all these contributions assembled in such a way that we can form a global matrix K T equal to G, where K is a global LHS matrix, left hand side matrix, which is a assemblage of the individual elements, individual elemental LHS matrices. So that means individual element we have seen, we get a left hand side matrix into, as I was saying, T1, T2, T3 equal to the known vector on the right hand side. So if we assemble all the individual element left hand side matrices, we get this global left hand side matrix. G is the global load vector. So right hand side known column vector is called load vector. So G is a global load vector, which is assemblage of the individual element load vectors, and T is a global unknown vector. As I mentioned earlier, that each node we are identifying as 1, 2, 3, either 1 or 2 or 3, and based on an element. But all these nodes, if we globally count, maybe there are 150 such nodes. So one node has an identification as a global node number. Also, it has identification as a local node number. It may be, node 1 of 10th element, node 2 of maybe 31st element, and maybe node 3 of 21st element. So this relationship has also to be explained or fed into the program. Now, global equation matrix in terms of nodal temperatures, we can this is what I was saying, K Tj. This Tj is maybe 1 to 150, 1 to 1000, depending on number of points in the domain, global points, equal to, and also that will depend whether we discretize the domain by triangular elements or quadrilaterals. That will decide total number of points, and Gi is the heat load vector. This we also explained in the last slide. Now, if we want to take care of radiation heat transfer, then obviously we have to write down the equation, which is Stefan-Boltzmann constant emissivity into T power 4 minus T infinity. This is local, ambient temperature, this is equal to TF here in this case, to the power 4, equal to HR. So this total radiative transport, if we write down the way we write convective transport, that means some transport coefficient into the temperature difference, then it is possible to write this way, HR, that is radiative heat transfer coefficient, into T minus T infinity. As such, there is no radiative heat transfer coefficient. The radiation is calculated this way. These are the properties. Emissivity is the surface property, sigma is the Stefan-Boltzmann constant, and then the fourth power of the temperature difference. But that is, we can model this way. If we model this way, then HR, the radiative heat transfer coefficient, will be defined. Obviously, we can find it out from here. Sigma into epsilon T star square plus T infinity square into T star plus T infinity, whereas T star is basically the gauge value of temperature. So this T, if we take as T star, then, and this T also T star, then this becomes the radiative heat transfer coefficient. So T star denoting the gauge value of T calculated from the previous iteration on the specified initial gauge or the specified initial gauge, and it will iteratively will correct till it reaches the final temperature. Therefore, the radiative total radiative heat transfer or the radiation integral, that becomes integrated again over the line element or the line segment, Ni HR T minus T infinity. Although HR, radiative heat transfer coefficient, varies over the length of the line element, due to variation in the value of T star, it may not be worth the trouble if the element sizes are not too large. So in such situation, this T star can be taken again Ti plus Tj by 2 or T1 plus T2. That means at the 2 points on the line segment divided by 2, and their basic initial temperature by 2, or either initial guess or the way it is evolving t star till it becomes t, where I and j are the nodes which make the concerned radiation boundary element. The same thing if it's a triangular element and the which are falling on the boundary, only their 2 points are lying on the boundary. That means one side is lying on the boundary, one segment is lying on the boundary, and that will have 2 points. That is the property of the boundary condition and property of the geometry. Now, see, we can, if we make the problem little more involved, we make it a unsteady state problem. We can write down the governing equation as rho c del temperature del time equal to k del square t plus q, and then again we can integrate it over the entire domain with the help of shape functions. Basic idea is if this if shape function is correct, temperature is correct, then eventually this integral will produce 0. So basically there will be no error will be minimized. So expanding temperature as NJ/Tj within each element, just the way we did in the earlier case, steady state conduction case, we can see all the terms are again coming. Only additional term is this unsteady arising out of unsteady term, that is rho c del temperature del T. So we are using here mass lumping concept, and we are lumping this and multiplying it with basically this T1, T2, T3, but its derivatives. So because these are this quantity is now time derivative. So del T1 del time, del T2 del time, del 3t del time, and rho c has been integrated over the domain using mass lumping concept. So that then produces C matrix. Basically, this integration produces C matrix into Tn. This Tn is dt dn, basically derivative quantities of the temperature. Then A Tn, this is temperature array, equal to B. So this also from local we can finally form the global matrix and global vector and global heat load vector. Now, in order to solve this, so this forming this C matrix, A matrix, B matrix, that is what is the major task. From each element contribution from each element, we get 3 by 3 matrix, and then all these matrices are globally added up and form the global matrix. And then again, this is unknown temperature equal to the load vector. This time derivative of temperature, also it is multiplied by the global matrix. So we have to now evaluate this. This evaluation, we can, in order to solve this equation, we can go for explicit formulation. Explicit, since this is mass lumping concept has been used, so here we can write basically T k plus 1 minus Tk by delta T, where k is the time level. And if we write that, so we can write tk plus 1 equal to tnk plus all the terms shifted to the right hand side, that function of tnk into delta t. Or the implicit formulation, implicit scheme we can write. Basically, I mean, here what we are doing, we are only writing this temperature derivative. That means T n dot can be written as Tnk plus 1 minus Tnk by delta T. And how that Tnk plus 1 can be evaluated in terms of Tnk and delta T, that basic scheme we have written here. It can be, this is, I mean, we already know this is purely explicit. This is fully implicit, because this T and K, if we write it at K plus 1 level, then it becomes fully implicit. And if we write, instead of writing this or this 44 or 45, if we write this Tn as average of two time levels, that means K plus 1 and K by 2, then it becomes, we have written here semi-implicit, or this is basically Crank-Nicolson implicit. So it depends the way we want to progress. Say for example, if we want to do it through implicit formulation, then in this C into Tn dot equal to A Tn equal to B, in this relationship, we can substitute what we have written for implicit formulation, that is Tnk plus 1 equal to Tnk plus Tnk plus 1 into delta T. And if we do that, then we will get equation 47 finally. And equation 47, you can see, can be solved for K plus 1 level temperatures. We can solve for K plus 1 level values from kth level values. So solving matrix 47, the temperature vector at the K plus 1th level and time level can be obtained knowing the kth level temperature vector. So that is the overall solution strategy. Now, instead of 3-noded element, we can have 4-noded quadrilaterals, where T can be given by, T can be expressed as Ax plus By plus Cxy plus T. Arbitrary quadrilateral, and again shape functions have to be determined, which are at different points. Shape functions will be ni, at this point will be having value 1, other points it will be having 0, n2 at this point it will be having value 1, other points it will be having value 0. Similarly n3 and n4. And first of all, we have to find it out the way we found out for triangular element, and then we have to perform the integration. So the shape functions n1, n2, n3, n4 for such a case will be obtained from, basically, if you recall, we obtain shape functions for triangular element as multiplication of xy1, one row matrix, multiplied by inverse of xi yi1, xjyj1, xkyk1, inverse of that matrix. So here also we will following almost similar procedure. It will be xy, xy1, this is the row matrix, multiplied by inverse of x1y1, x1y11, x2y2, x2y21, x3y3, x3y31, x4y4, x4 y4 1. Inverse of that. In the similar process, we can find out the shape functions. Similarly, if we take a six-noded triangle, the shape function, just we add three more nodes on a triangular element, and then the shape functions can be n1, n2, 2, n6, and this will be given by x square, y square, xy, xy1, this row multiplied by inverse of this matrix. And there the temperature interpolation is given by this polynomial ax square plus by square plus cxy plus dx plus ey plus f. The size of the elemental matrices will also be different for higher order elements. So now we have understood overall formulation strategy of finite element method and how it differs from finite difference and finite volume method. We mentioned finite volume is finite difference is basically difference quotient based method, whereas finite volume is basically integral method, but the weighting function is 1 for each integral, and finite element is again integral method to minimize the error, and here this is also a subdomain method, but this weighting function has to be determined, and when we use Galerkin weighted residual method, this weighting function is exactly equal to shape function. So how to really, now you can see that, or we can understand that in this entire formulation, the relationship between the nodes, the local nodes, that means local nodes of the elements, and the global node number, these are interrelated, and these have to be sort of identified and stored somewhere, and this will help us to form the global matrix, global unknown vector, and global this load vector. So this bookkeeping is done through some data structure. I have given here a very elementary way, so that a very elementary way of understanding, and very easy example to follow. See, if IEN is an array which is connectivity array, creates a connection between local node and global node. So IEN node will be written in this way: NEI 1 N 1 colon NEN, comma 1 colon NEL, whereas NEN is the number of local nodes and NEL is the number of elements. Just listen to this. We will take up an example, then it will be, we'll take up an example and then it will be clear. Now, ID is an array that is called destination array. This establishes the relationship between global node number and the equation number. Sorry, the screen was a little disturbed. I think you are settled again. So IEN array is the local node number and the element number. relationship between them. And second is an array, which is basically, will identified by the global points. That means, and it will assign some value to the global points. This will assign either value p or 0. P is any integer, denotes the equation number from which equation it has come, or it connects to some specific equation, and that connection. And 0 is if it is not connected to any equation, and usually these are Dirichlet boundary conditions. The boundary values are always specified. In such cases, no computation is needed. There will be no equation number. And another array is LM array. The location matrix array establishes connection between, again, element number to equation number through the local node number. So that is why here this is En, which is basically a local node number, and El, which is basically the element number. So LM array uses ID and IEN arrays. It determines the position where each element of elemental matrix will be placed in the global matrix. So the relationship is established through these arrays. So this is global node, this is equation, this is element. These two are connected by LM array, these two are connected by IEN array, and these two are connected by ID array. Now we'll take a very easy example. See, there is a square domain and it has 4 triangles, and one side boundary is specified, that is Dirichlet boundary condition. We know the temperature here. Another side, again, temperature is specified. So these two sides are temperature specified. These two sides may be insulated boundary. Now, since the domain is divided by 4 triangular elements, element 1, element 2, element 3, element 4. And global nodes, first let us understand. 1, this is obviously globally 1 node. This is globally 2 node. This is globally 3rd node. This is globally 4th node. And this is globally 5th node. So in the overall geometry, we have only these 5 global nodes, 1, 2, 3, 4, 5. Now if we separate out elements, for example, element 1 we are separating out, and any element will have only 3 nodes, 1, 2, 3. So this square denotes local node number, and this circle denotes element number. So this is first element. We have taken out first element through the circle. Local node number 1, local node number 2, local node number 3. And this node, its global identification is 1. This node, its global identification 2, but this node's global identification is 5. Then we are going at the second element. Second element, again, element, circle denotes the element number. This is second element. And for this second element, the local nodes are 1, 2, 3. But the global nodes, this is global node 2. This belongs to, this side. So basically, this 2 is a local node, but its global identification is 3, global node. Here, 3 is the local node number, but its global node number is 5. Now take the third element. This is the element number. Again 1, 2, 3. These are the local node numbers. But with respect to global node numbers, this is 3, this is 4, this is 5. Finally, the fourth element, element 4, 1, 2, 3 are the local node numbers, but global node numbers are 1, 5, 4. So the NEN, that is number of nodes, local nodes 3, number of elements 4, and number of global node numbers are 5. And then when you read, you have to use this slide for the next slide. Without looking at this slide, next slide cannot be made. So back and forth you have to keep looking. If you form IEN array, this direction is basically number of elements, and this direction is number of nodes. So first, second, third, fourth, these 4 elements, first, second, third, fourth, and for each element we have node numbers 1, 2, 3, but this at this position we will write the global node number. So when 1 is the element number and 1 is the local node number of the first element, then what is the global node number of that? It is 2. It is, what did I say? It is 1. It is 1. So this is the element number 1, and it's local node number 1. So what is its global node number? That is also 1. Then element 2, its local node number 1. So element 2, its local node number 1. What is its global node number? 2. So global node number 2. Element 3, its local node number 1. Let us look at it. Element 3, local node number 1, but its global node number 3. So here entry will be 3. Similarly, element 4, its local node number 1 is this node, but this node is basically globally number 4. So globally number 4. Similarly, again the first element, local node 2, global, what are the global node numbers? Third element, second element, second local node number, what is the global node number? So third element, again second local node number, what is the global node number? So this way we have to fill out this table. So this array is called IEN array. Second array is ID. ID, as I said earlier, that it whether the nodes are connected with the equation or not, that is what it writes. So 1, 2, 3, 4, 5. Here 1 we can see it is falling on specified temperature boundary. 3, 4 is also falling on specified temperature boundary. So no computation is needed. It is directly known, and for 5 computation is needed, and we are writing it 0, 0, 0 for 1, 2, 3, 4 nodes, and for 5th node we are writing 1. 1 is the equation number. I have just given. It can be any, the way we define equation numbers. It is connected to equation, and that equation, but 1 means it is connected to equation. Similarly, now we will go for third array, LM array, as we defined here. This is basically LM array, and here this is element number, this is the local node number of the element, but whether that node of that element needs equation or not. So first element, first node doesn't need equation. Similarly, second element, first node, it is node 2, does not need equation falling on the boundary. Third element, again node 1, it is 0.3 falling on the boundary, doesn't need equation. So that is how we are progressing. Now, this is NP. NP is, I've done a small mistake, not small, I mean, I've done a mistake. NP is the global node points. NP is basically identification of, you read this again, because without looking into the previous slide, I mentioned you earlier, one may commit mistake like I did. NP is the global node number. So first global node number, and it is very clear then, we don't need equation. Second, we don't need equation. Third, we don't need equation. Fourth, we don't need equation. Point number 5, we need equation. So point number 5, we need equation. And this is basically element, node number, whether we need equation for that particular node number for a given element or not. We need equation or not. Here, first element, first node, we don't need equation. Second element, first node. So all elements, first node, we don't need equation. So that means this element, first node, local first node, is falling here, we don't need equation. Second element, local first node, that means 0.2, we do not need equation. Third element, 1 means global 3, we known. Fourth element, 1 means global 4, known, we do not need equation. Similarly, first element node 2, second element node 2, third element node 2, fourth element node 2, we have to see whether we need equation. But first element node 3, second element node 3, third element node 3, fourth element node 3. All these nodes are basically fifth node. First element node 3 is fifth, second element node 3 is fifth, third element node 3 is node 5. Fourth element node 3 is node 5, and we need the equation for all this. And this is how these arrays are formed. These arrays govern formation of, as I have said, formation of the global matrix. The connectivity array, this creates connection between local node and global node, and these arrays are needed to form the global matrix, then global unknown vector and global known vector, or the load vector. So as I said, that this effort was to give an introduction to finite element method. We have not taken up any specific problem. If we take up a specific problem, things will be more clear. If we get a few more lectures after covering the basic whatever is needed for this course. If we get time, we'll fall back with specific problem so that you can get hands-on experience. But now you know overall how a problem can be handled by finite element methods. And my class notes that I used, these are prepared from these two books, very well-known books. One is Fundamentals of the Finite Element Method for Heat and Fluid Flow, Luis Nityarasu and Sitaramu. And the second is Introduction to Finite Elements in Engineering, Chandru Patla and Belegundu. This is also a very well-known book. So you can consult these two books. I will also circulate the notes. And as I said, the basic idea of formulating a problem based on finite difference, finite volume, and finite element, that was the initial target of our first few lectures, or the first 3 modules, you can say. First module was based on how finite difference works and what is the best way to implement finite difference philosophy, then finite volume, and then now we have completed finite elements. From here onwards, we will go for full-fledged solvers for different flow and heat transfer situations. I'll stop here today. Thank you very much. Thank you.